Why should you have an integration? Well, the timelines, these are shortening each time, and parallel development of both your solid state chemistry and your process development, that saves time. I will show a small graph in the next slide. The early integration of solid state chemistry and process chemistry gives a chance to have a good risk management of your drug development. You have already an idea what is possible, what are the dangers that you get when you scale up. Are you going to see multiple polymorphs? Problems with isolation, filtration can be very slow. These are things that may occur when you scale up and when you go further in your drug development. So as soon as you know that it may occur, you can have an idea on how to approach that problem at the earliest possible stage. When you couple both, you have already the idea of the problems, but also your result will be a better production process and a better quality material at an earlier stage. You cannot optimize a process and have crappy material at the end. You need to have a good material because that means that you had a good process. You thought about as well the chemistry as well as the physical form of your compound. Very short timelines. Well, it's clear that when you integrate solid state, then you can do it in parallel, and some things are not needed anymore. Handover of any information is much easier than when you have two different companies who work on this one. Characterization of the material is not needed because that is done already while the process development is ongoing. As soon as in the process a problem arises, you can step in and say, okay, this is needed to get the process going again. And that can be after a few weeks, it can be needed from the start. So you can save up to 3 months of development time here when you have this integrated approach. But most of the time it can take up to several months, up to a year, which delay you will have because you go from process development, it doesn't work, you first have some solid state going on, back to process development, have to repeat certain things, not optimal, and so on. That is something that really, well, it is to avoid, and by the integrated approach, you can indeed avoid that one. So we have two approaches at CML here. When a process is already optimized or when it is fixed, we only have a look at the form. So form select means that most of the time the HCl salt or the free form is taken as default. So you can make an HCl salt out of it. Okay, let's take this one. We go forward with it because we always do that. Many of these compounds, they are not optimal because also HCl salts have the tendency to be hygroscopic or to form hydrates, and that can be uncontrolled hydrates. So you do not have a good idea what actually the active ingredient is when you have a mass of API there. So it is not an optimal situation when you just take each time the HCl salt or the free form. The choice of solvents, the choice of salt and the choice of solvent from which you get it greatly improves your properties, and that can be solubility or stability. When you look at the earliest possible development phase to this form, you can have an effect on the crystallization and to see which forms or which salts can be selected to study in parallel, and then make a selection, because the aim is to compare these properties and select the most optimal form. The process is already fixed. Details are there if you make a salt out of it or you have a recrystallization going on. I will show a typical program which is when you have a look at possibility to form any salts, it is about 12 to 24 counterions and the free molecule itself. 2 to 4 solvents, including water and methanol. Water is very important here because everything turns on the aqueous solubility. That is the main point here. If you want to make a tablet, it has to be soluble in water. Otherwise, you will have huge problems to get it to be active at the right side there. Dissolution rate comes at a later stage, but it is as equally important, of course. When you have a look at which methods to use, well, 1 or 2 methods. If it is a very insoluble compound, you just go to slurry at different temperatures. When you have a choice of different solvents which you can use, then you have cooling crystallization, which most of the time improves your quality of your salt. The ranking criteria, because you are not putting absolute values there, you are looking at which one is best to take forward. It's very much depending on what do you want to do with it. It depends on which property you want to improve. So you can have a look at crystallinity, you can have a look at aqueous solubility, or you can have a look at stability. All of the ranking criteria needs to be looked at before you start the program, because if you have a problem with your solubility, the choice of your counterions will be such that in general these counterions will improve the solubility. And when you know it doesn't want to crystallize, you go to larger counterions or find a way to influence your nucleation behavior and to crystallize it in a better way. The second approach that we have is when next to the choice of your compound, of the form of the compound, you also have to develop a process. So when you have a problem with the yield that you get, or that you don't know exactly when the end is of your reaction which is going there, you have possibly something which is well, very difficult to filtrate, and impurities of each batch are different, or you just have a poor quality material. So all these things may occur in the process, and when you look only at the chemistry and you try to solve it, of course you can improve, but maybe you cannot solve the real problem which is behind this. And that can be that either your crystallization is not okay, your form is not consistent each time, you have mixtures, you have a lot of amorphous material available. These are all things that may occur. So that is why we combine process chemistry and crystallization science, and by working together in this process, on each and every step you can improve both. You can improve the chemistry and you can improve the solid state. So the aim is smoothen this R&D route to optimize the end product, but also have a look at what is the process time, what is the yield, other things that are important, which depending on what do you need to improve there. I have 4 examples here on how to do it. You can have a look at the yield. So by looking at your metastable zone with again, you can calculate how much will be present at high temperature, how much will be present at your low temperature, room temperature or anything, and the difference is how much yield can you get. Maybe you have to select a different solvent if your nucleation curve is very flat and you cannot get a lot of material out of your solvent by just cooling down. Your cooling conditions can be very important. How far to cool down, but also how fast. Seeding can be important. Sometimes you just get a little bit of hazy solution and it doesn't really want to crystallize. You go down far below zero and finally it crashes out and you have a poor quality material. If you seed, you can control it better. Control means that you can get a good material out. maybe an anti-solvent needs to be added. If a lot of material still remains in your solvent in solution, then anti-solvent may help you there. Filtration, of course, each time, each process has some of these bottlenecks where you have poor filtration, where you have a very needle-shaped morphology of your crystals, and these block your filters completely. So you have to wait for days before something is really filtrated or before everything is dry. So the conditions on which filter to use, pressure, temperature, that can already have an influence, but also which solvent to use for the filtration, for the isolation of your material, and which solvent to use to dry it, to help it dry. Maybe anti-solvent can help there and even wash away all the impurities that you have. But mainly control of the particle habit, and that means the shape and the size. That one is very important in filtration, to improve your filtration rate and to improve your drying properties. The stability of your particle is one of the issues there. Purification. Of course, recrystallization is easily added. You have a process and in the end you don't have a pure product. Well, add another step in recrystallization. But you can also think of remove this impurity at the moment that it is produced, and if it cannot be isolated from your product at that moment, look at different forms, look at intermediate salts, look at possible solvates. For an intermediate, it is not important what the form actually is. If it is most stable for years, no, you just want to have a purification step and immediately go on with the process. So select the process step in which you can remove these impurities as easy as possible. And the final product, there it's different because the API has to have as less residual solvent as possible, as less as impurities as possible, and to have a homogeneous particle size distribution as much as possible, of course. So when you selectively and controlled crystallize the form, you can have a better improved product. These are separate steps, and the process itself determines which steps